Okay, guys. Middle carbon is sp. It has two p orbitals. If we draw this, we got the one carbon, trigonal planar. There's the trigonal planar. It's bonded to this carbon over here, and that's bonded to the other carbon. Trigonal planar, sp2, with a p orbital. We can draw the p orbital there. All right. This guy has how many p orbitals in the middle? Two. One of them we can draw like this. Now let's pretend these are straight up. If those are straight up, the trigonal planar is perpendicular to it. So this is like this is going back, and this is coming forward. So it's like the trigonal planar is like this. Now the p orbital is straight up. And this can overlap and make the double bond. This has another p orbital. How's the other p orbital oriented? Perpendicular to that, or orthogonal. Okay, your three p orbitals, look back at GenChem, they're all 90 degrees to each other. One of them has been removed and hybridized, but the other two are still 90 degrees to each other. The other p orbital is coming out at you and going back into the board, back in the hull. Okay, it's sitting like this. That means, now this one has a p orbital, but this p orbital is going to interact with the other one there. So these two are actually sticking out. And if they're out, that means if they're like this, the trigonal planar is straight up and down. So these are actually straight up and down. And I can't draw this, but pretend there's two p orbitals out and back through the hull. Now, if these are like this, are they overlapping with those?
Why isn't that one an up and down?
Why is what one?
The last?
Well, because it's interacting not with that. This says you don't have three interacting in this one with a single electron. This single electron in this p orbital always wants to overlap with something. So it overlaps here. And you make pi bond here. It's two separate systems. The two pi systems are 90 degrees to each other. You have one pi system flat on the board. The other pi system, the p orbitals are turned, and so it's like this. But this pi system is not interacting with this pi system. Because for this to interact with this, it has to be straight up. Because p orbitals have to be straight up to interact. Okay? This is a subtle, not too subtle, but it's a secondary point. These p orbitals are interacting, but if that one's turned, even though it's on the adjacent carbon, they're no longer interacting. Okay? So not only do they have to be adjacent, they also have to be all lined up, like toy soldiers standing up. Question?
Is there any way to draw those ones that are coming out?
I mean, you can. Usually this would be done sort of charted like, okay, I can't really draw it straight out, but those are interacting separately. It just doesn't look, if I can get a 3D picture with some color, like in the textbook, you can kind of sort of see the planes, but it's just kind of turned. And that's called cumulated. But it's a good structural exercise to understand how the orbitals are oriented. Sophia?
Okay, so why isn't the last one, because the other two have, I'm just confused why they're only going.
If I put this one straight up, each one has an electron, right?
Yeah, because the middle one has those two.
Middle one has two. Electron overlapping with electron, making pi bond. What is this going to interact to make pi bond? It's going to turn and interact with the other one that needs to make a bond. See, these need to team up.
But so the last one doesn't have any going up and down like the middle one does?
No, it doesn't. It only has one. That's a good point. It only has one, but the middle one has two, like this. But the top, but there it is like that in the middle. This one is making a pi bond over here, and they're teaming up and making that fabulous bond. And this one over here is like, okay, I'm going to make a bond. But see, this guy has a single electron. And so it just sits there, and this single electron teams up with that single electron, and you make pi bond like this. The system is not going to let this interact with those two and let that sit there with a single electron. It drives the bonding, and thus you end up with here. If I had another finger, I'd hold it up over there. The other is like this. Okay? It's called cumulated. They're not conjugated. Okay, benzene is a fully conjugated cyclic system. All these are conjugated here. You could draw that. That's 6 p orbitals all lined up. Okay? It's a granddaddy of called aromatic. Once it's cyclic, it takes on very stable properties. We covered that in organic 2. Different chemistry in alkene. We never really cover these guys up here. That's an oddity. It's a good structural. Understanding this concept, heats of hydrogenation, stability. Let's go down to resonance structures, showing dipolar resonance structures. Look at this diene, okay? One thing we need to do is just take stock or counting of what we have here. How many p orbitals are conjugated here? And we have a pi system. How many p orbitals? 4 p orbitals. Okay? How many pi electrons? That is, how many electrons in the pi system?
8.
Why do you say 8?
2 per.
Then each one of that one.
I mean, it's the same as no, it's not 8. We got 4 p orbitals, and the pi bond is made from what? One electron overlapping, right? One electron overlapping, right? Okay, there it is. How many p orbitals?
4.
How many electrons? 4. Okay. Okay, showing dipolar resonance structures. Now, showing resonance structures with just these hydrocarbons is going to be a little bit difficult in that it's not intuitive. You're almost like, why are we doing that? It'll be easier when we have like an oxygen. Because if you put an oxygen here, then we have dipole, and we can move electrons towards the oxygen. I'm going to move electrons here, but you're going to say, why'd you move it towards that carbon? Well, you can do it either way, okay? But this is going to be theory. And I cover resonance 2 different ways. A lot of theory, orbitals, how they are, okay? But then we'll do the work and like show resonance structures. And what do you need to do what are you going to see on the test? And how do you do it to illustrate? So you got the theory and then sort of the illustration and doing it. All right, one thing in the theory is understand your pi system. 4 p orbitals, 4 electrons. Now really, when we have the pi system here, it becomes one system. And I described this earlier on as if we have a garden hose that's 10 feet long, or let's call it 4 feet long, and you put water in it, how's the water going to spread out in the garden hose? And you cap each end, and you lay it flat, how's the water going to spread out? It'll spread out all in there. That's sort of what we got here. Those 4 electrons really spread out all in that system. Now, what if I take the garden hose that has the water equally spread out and I lift one end up? What will happen to the water?
Like that to one side.
It'll migrate, most of the water will go to one side. That's analogous to me putting in a heteroatom like an oxygen. If I put an oxygen on one end, what will that cause the electrons in the system to do?
Go to that end.
Go to that end, to a degree. And we can start showing structures that illustrate that, and then as the electrons move to that end, charge minus charge starts building up at that end. So this is sort of the theory. But how do we do this on the board and stuff? Okay, well, one thing I want to show you is, really, whenever you do your so-called resonance structures, you got your pi system up there. And really, put your 4 electrons in. And you can put them in any way you want. And everywhere you put them in, that's just going to be a different so-called resonance structure. I can put 1 in each, but then I'll get what I just had here. Because I'm going to erase this real quick, but if I put 1 in each, then I can say, well, these could overlap and make a pi bond, and those could overlap and make a pi bond. And if I do that, that looks like pi bond here and here. That's that structure there. Question?
So these orbitals that you're drawing are really just a representation of like where the probability of the electron is going to be, and the wider it is, there's a greater one. So what would an actual orbital look like in this resonance structure, I guess, since that would be, basically it would almost...
So you really get into molecular orbitals. Okay? You need to look at molecular orbitals. We're really moving into that to a degree, but we're not saying we are. We're still maintaining individual. Everything I do will maintain individual atomic p orbitals, but really we're doing molecular orbitals. You're getting into that. I'm sticking with the isolated p orbitals. Okay, let's put them in another way. For example, maybe I put 2 here. And put 1 there and 1 there. That's 4. What does that give? If we were to draw this as a fixed structure, well, 1 here and 1 here looks like pi bond. There's none there, and there's what here? 2. And so this is, now we got charge. And that'd be minus, what would this be? There's 1 H there, but it's missing a bond and an electron, so what's that? That's a positive.
Why aren't the ones in the middle overlapping? The 2 in the middle?
They're all overlapping, it's just I'm showing. Your question is like this, why aren't those overlapping?
Were they?
They actually are. All these are. But I was showing isolated. I was showing you make pi bond here, pi bond. See, this is an isolated fake structure. Okay? I'm showing you like, okay, that looks like the pi bond. 1 electron making a pi bond. I drew that. But this, I didn't erase that. Ultimately, it looks like a pi bond and a lone pair. Well, guess what? That's a resonance structure. That's an alternative Lewis structure there. It's a resonance structure there.
What is does that not change the geometry of that last carbon?
No. Why would it change the geometry? What's the hybridization of this carbon? What is it here? sp2. I'll get rid of that. What is the geometry here?
Presumably sp2 doesn't change if it has 2 hydrogens.
Yeah, there are 2 H's there. What's the hybridization here? No, it's sp2. Why is it sp2?
Is there anything in the orbital that seems like we naturally want to shift over to an sp3 to make that worse?
No. What do we say about a lone pair next to a p orbital? Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital?
Yeah.
Is there a p orbital here? What's the hybridization of that carbon? sp2 with an empty p orbital. This lone pair is going to be in a p orbital. See, that's why I taught you that 2 weeks ago, so we don't have to change that. Right? Yeah. A lone pair is in a p orbital. Like we talked about a week and a half, 2 weeks ago. Everything we talked about before is leading up to what we're talking about today. Okay, draw another resonance structure. Well, I could draw, let's put 1 there, and, well, let's do this. Let's put 2 there and 2 here. I mean, this is going to be a resonance structure. This is going to be pretty ugly, though. That's going to be what? I don't have any isolated pi bonds. You see any traditional pi bonds? No, I have a lone pair and a lone pair. What is this? That's actually a resonance structure. What I'm illustrating here, you can put your electrons in any way. But what we ask is, well, which is the best way? Well, of the two we did here, which do you like better? I really hate this. You see, this is a bad resonance structure. This is not going to be called major resonance structure. Okay? This one's better. Now, which one do you like better? This one? Or do you like this where we put one in each? See, this is your major resonance structure. That's why it's drawn like that. Usually we draw major resonance structures. Take home point. What we have here is 4 p orbitals, and you got 4 electrons in there. But they're spread out all through there. Okay? This is a local, what do you mean localized? This looks like the pi bonds are right there, and there's nothing else going on. That's not right. There's plenty else going on. There's continuous overlap. We have one pi system, the electrons spread out. Now, that's some theory. Let's do it as if, okay, how do you do this and just show it without being so broadly theoretical? You can polarize a pi bond, okay? We can just take these electrons and let's just kind of back them up and move them onto the carbon as a pi bond. What does that give? It's going to give a resonance structure. This is your resonance arrow, double-headed resonance arrow. What does this arrow mean? Well, I haven't done anything over there. What does it mean to you? Here's the double bond. Somebody take this and just move it over here, and now it's sitting over here as what? As a lone pair. Now, what is this? Positive. It's a resonance structure. But isn't this what we drew down here? Okay? But the way I'm doing it here is more of the, okay, let's do our arrows and let's do it a little bit cleaner. But understand what we're doing. I polarized, be a polarized resonance structure. But see, the question you might ask is, why would this do this? You don't really have a dipole here. Why would this carbon want to take home minus? That's why I explained at the beginning. It's going to look a little bit like, why are we doing this? One last thing we need to say here is, well, let's move down here. Resonance hybrids. True structure, including partial charges. Let's keep going here. Let's keep going here. One thing we'll do lots of is sort of just keep going. Let's look over here. We got a plus charge. These electrons can now move over here, and I will call this sort of like a windshield wiper. Okay? What does that arrow mean? What does that now give? Show the result of that. Well, we didn't do anything with that lone pair. What does this mean? Okay, it's not all moving over there, it's just windshield wipering. And so now we have pi bond here, and now what's here? Now positive. Now all of your resonance structures are going to illustrate the true structure. None of them are exactly the true structure, but the true structure all has qualities of it. But what do you see right here? I see double bonding between the two middle carbons. We see it right there in that fake structure. But didn't we say that earlier? Isn't there p overlap between the two middle carbons? We see it illustrated right there. Okay? Polarized structures. What is the true structure? The true structure is a blend of these. full double bond. But look over here. It's not full double bond there. It's not full double bond there. Thus it has some single bond character. And so the bond order, is it 2 or less than 2? Yeah. It's less than 2. See, if we looked at this, and if we said it was if that was the structure and it was just fixed like that, it looks like a double bond with bond order of 2. That looks like a single bond with bond order of 1. But no, it's less than 2. What do you know about this bond order? Is it 1 or is it more than 1? It's more than 1 because we have some pi overlap there. As I already told you there, and as seen in that fake structure. So this bond order is greater than 1. Now your bond order is going to equate to your bond lengths. Since this is greater than 1, is this single bond here longer or shorter than most single bonds? The more the bond order, the more double bonding. And the more double bonding, the shorter you get. Because double bonds using sp2, okay? All right? So this bond here is really shorter than just a true single bond. Okay, in the end, dealing with this here, it's very theoretical. Let's move on, and a lot of this stuff we'll do again, and it'll be a little bit more crisper and cleaner and clearer when we start doing heteroatoms. Okay, and we'll move away from just pure theory into this, let's do it. All right, let's go down here. Resin stabilization of cations. Got one drawn here. Here's a carbocation. I did it right here. And the question I'm going to ask you, and we got to make sure we know, is how do you stabilize a carbocation? Do you move electrons towards it or away? Towards it. It needs electrons. So, I could get, if you go back over here, I can give this electrons by doing the windshield wiper. That gives that. I could also give it electrons by moving these in, but that would have taken us back to the original structure. Do it down here. Show a resonance structure. Well, windshield wiper. These electrons move here. What do you get? Now you got double bond here, and what's here? Positive.
You could end up where you started doing that.
It looks, those look very similar, don't they? Okay? Which is the major resonance structure? Which do you like better? Exactly. These we would call equal contributors. Yeah, they have the same energy. Equal contributors. Now when we have equal contributors, what does the true structure look like? Well, let's look. It's just a blend. What's the blend of a single bond and double bond? You average that together. Bond and a half. What we have here is BO here equals what? 1.5. Okay, what's the BO over here? Double bond and single. What's the exact average? 1.5. This is a 50-50 blend. Now, charge. Now, since this is 1.5, you often see this drawn like 1.5. 1.5. Now, charge. We can also do a hybrid of that, or a blend, or average it. This carbon has a full plus. There it's neutral. What's the average of +1 and neutral? Half a plus. I'm going to do partial plus. That carbon has only a half a plus. What about this one over here? Partial plus. Which CC bond is longer, the one on the left or right? They're the same. This is your true structure. This is called your resonance hybrid, but it's also your true structure. Thus, anytime someone shows you that, you have to say, hey, that's just an isolated depiction of the true structure. I know, what do I know? I know it's really that over there. Here's the difficulty. This can be very cumbersome to draw and work with. Because of that, instead of drawing that, we just draw these two, which are much cleaner and easier to work with. But we have to say, these are fake, isolated structures. The true structure is hybrid. This is analogous to the red and white and pink. Whenever you look at pink, that's pink. And this is like red and white. What if pink was hard to draw and instead I said, here's red and here's white? Can you imagine that if we blended these, you'd get pink? You could do that, couldn't you? That's what we're doing. Now when you look at pink, also, these are resonance structures, resonance areas. Are these in equilibrium? No. That's it. If you could look at this structure, that's it. It doesn't change. It's pink. Now when you look at pink, is it an equilibrium between red and white? And it's so fast that you can't see it? No, it's just pink. There's no equilibrium. Resonance structures are not in equilibrium. We don't use equilibrium arrow, it's resonance arrow. These are fake. Questions up to this point? Seems like with that example right there, we covered things in more than a nutshell. Important term here is, we say this charge is delocalized. Is that charge sitting right there on that end carbon? No, it's really spread over two different carbons. That's going to stabilize it. Resonance stabilization of carbocations, right there. But didn't we do that before? We did that twice before at least. Question?
Will we be going to, will we also be going from the hybridized resonance back to the things that like combine to make?
That'd be a good exercise to do, but traditionally, it's usually show the hybrid type questions. But that'd be a great thing to be able to do. If you were given this, could you show a fake structure? Okay. All right. How do you stabilize a cation? Move electrons towards it. Okay. By the way, in the back here, there's a list of rules. Usually I put this on golden paper because these are your golden rules of resonance. Okay. Many things we will say are summarized right there. For example, one thing we will say is all of your fake resonance structures should have the same charge. That has a plus, so that has a plus. All resonance structures have the same net charge. Okay? There's many other things over there. Bonding do not change. Let's summarize this. Whenever we draw resonance structures, what changes? What's the difference? What has changed? Has any atoms moved? No. What is moved? Only electrons. What type of electrons move? Sigma or pi? There you go. Resonance structures only differ in placement of pi electrons. Everything else is the same. Pi electron. Don't go moving any sigma electrons. If you do, you'll be making a new compound. You won't be making a resonance structure. Okay. Down here, we can draw at least, I think, 3 additional resonance structures. Draw the 3 additional resonance structures down there. I would start with this. How do you stabilize a cation? And remember the windshield wiper. There you go. And use your arrows and do everything with arrow movement. Good. That's good. You can do that. All resin structures have the same net charge, so if that's plus, you got a plus over here. Okay, hopefully you have at least 1, 2, or more. First off, little theory. Let's talk about the pi system. Okay? How many p orbitals are all conjugated here? 7 p orbitals. How many electrons in the pi system? 6 pi electrons. 2, 4, 6. Is there an electron there? No. What do we have here? Real quick, let's just draw the pi system. See, this is the benzene ring. It's got 6 p orbitals. They're all sp2. I mean, one electron makes pi bond, one electron makes pi bond, one electron makes pi bond. There's your 3 pi bonds. But then we have this over here. There's one H there. It's a plus charge. What's hybridization? sp2 with a p orbital. What's in the p orbital? It's empty, but it's still there. But see, all these are overlapping. These 6 are overlapping. That makes it aromatic, but it's also overlapping with that. There's your 7 p orbitals all overlapping. How many electrons in the system?
6.
Here you go. There's your pi system. Okay, help you know your structures, starting point. All right. Now I can go back and say, okay, let's put the pi system. Let's put 6 electrons in there any way you want. We can do that very theoretically. But instead, let's get to those resonance structures by moving arrows. And this is a cation. And I told you how you stabilize cation. With electrons towards it. And with pi bonds, we can just do a windshield wiper. Boop. All right, move these over here. What does that give? Boop. Pi bond now. We didn't do anything with that pi bond or that pi bond. What's here? Positive. Okay. Can you keep going? What if we move those up here? Use your arrows. What does that give? It's going to give another alternative Lewis structure where all we moved is pi electrons, also known as resonance structure. So now, what does this arrow mean? It means we now have pi bond up there, and what's this? Okay, that looks sound ugly. Everybody know what I'm doing here? All right. We can do one more, because these can all right, what can we do now? Well, we could go boop. And if we brought that down, what would we get back? We go back to the original. How many total resonance structures? 4. Now, it's actually, you could actually show more than 4, but the others would be ugly. Because I could put the electrons in there many other ways. But I would end up with 3 charges.
It seems like just drawing a 4, that would favor the electron being in the pi bond between the outside of the ring, but would it actually be?
Okay, it actually does. Here's the reason why. Because that benzene ring is very stable. It wants to stay like that. Okay? Which is major? They all have 1 charge. We'll see other things for looking for major. But here, this is actually major. Yeah, you're right.
Should the greater charge would be outside?
Probably. Because this wants to maintain, it's like leave me alone, I'm aromatic. I'll stabilize you by donating my electrons by resonance. But what would the hybrid look like? Let's assume that they're all kind of equal contributors. What's the hybrid look like? Well, you do that by drawing your, what do we want to call it if we just showed that? Just want to call it the compound without the pi system? What else could we call it? What bonds am I showing here if I don't show the pi system? Sigma. Yeah, this is the sigma complex. Well, this complex is something else. Sigma, no, this is it. It's the sigma framework. That's what we can call it. Does that make sense? Okay, there's your sigma framework. Show the hybrid, the partial bonding. What's the bonding between carbon 1 and 2? Is it single or double? Now it looks like there's more double. Well, let's just say it's, what's blend between the single and double? Somewhere in between. See, it's somewhere in between. I'm not saying it's exactly 1.5. Now what's the blend between double and single? Somewhere in between. What's the blend between single? Well, that's still single. But we got some double bond character. What's the blend between single and double? Somewhere in between. Guess what? You can do this all the way around. You're going to get bonding not single, not double, but somewhere in between. Somewhat like a bond and a half. We get this like this. Charge. Is that a full plus or is it partial plus? Well, it's full there, but you see it takes on neutral as you get to the electrons distributed. Partial plus. Which atoms have partial plus? Not all of them. Which atoms took on pluses? That one. Did that atom ever take on a plus? No. So we never draw a partial plus there, but the others did. 4 atoms took on partial plus. Now this is your, it's more than just sigma framework. What am I going to call this? Resonance hybrid. That's approximating the true structure if you could really see these electrons. Okay? Again, this is cumbersome though. We work with fake structures. We think of the blend. But when we do chemistry, we'll actually do chemistry with these because they're easy to work with. Okay.
So those ones never take on a partial plus from the geometry of the system, or just the way we do it? There would be...
Based on simple resonance theory that we're talking, they do not. Now, deeper considerations, you could make an argument. Okay. But my answer is no, they do not. For us. Okay. How else can you stabilize the cation? We stabilize it here using a pi bond. You can also stabilize using lone pair. Lone pair. See, now we got a lone pair next to it. What's the hybridization of that oxygen? Hybridization of the oxygen?
SP2.
SP2. Why? Carbocation has an empty p orbital. And anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital. Right? All right, so we don't have to. And that's why, this is why. Okay, pi system, how many p orbitals are we dealing with? Well, let's draw it. The oxygen is trigonal planar. This other carbon is trigonal planar. There's also an H there. What else is also on the oxygen? Hold on. That's a lone pair. One lone pair is there. There's a trigonal planar. One more lone pair. See, the other lone pair is in a p orbital. And what do we have over here? Just a p orbital. See the sigma framework, trigonal planar? P orbitals left over. Why does this lone pair want to be in a p orbital? So it can pi bond. We learned that 2 weeks ago. See, there's really pi bonding between here. Let's show the pi bonding by showing a resonance structure. These electrons, we're just going to move them in and make pi bond. That's going to lead to, right there, one lone pair. All resonance structures have the same net charge, so if that's positive, this has to be positive. Where's the positive? On the oxygen. And we call that the so-called resonance structure. To illustrate this, this is really the hybrid. We draw the hybrid more conventionally with just partial bonds. Is this a single bond, double bond, or what? What's the average of double and single? Yeah. Now, is this carbon full plus or partial plus? Partial plus. It's an average of plus and neutral. How about the oxygen? Partial plus. See, there's your hybrid. There's actually some pi bonding. The oxygen is helping that carbon out. Here we can say which is major and which is minor. Which is your major resonance structure, your best one? Which one you like best? Which one you like best? This is major. We call this minor. That means that the hybrid looks more like which one? Yeah, it's not a perfect blend. The hybrid looks more like the major one. Kind of like the baby looking more like mom. Because mom's more stable. Mom's pretty. Why is it major? Because it has more bonds. Doesn't it? I mean, this one has the extra pi bond. Not here. Major, more bonds. More bonds makes it more stable. What's an argument for it not being the major one? Brianna? Oxygen is a greedy little electron, right? Oxygen doesn't like becoming positives. But see, oxygen also has a kind heart. And it sees that carbocation over there, and it's like, I don't like becoming positive, but I'm going to share with you. Okay? So there's some conflict here. Here's the take home. More bonds, major. Okay? When this is important, and it's only golden sheet of rules. It's okay for oxygen and even fluorine. Chlorine to take on positive, as long as they keep their octet. Does oxygen still have an octet over here? Yes. Still has octet. And so it's okay, and it's actually good. Never show an electronegative heteroatom like oxygen, fluorine, chlorine without an octet. If you do that, they'll hunt you down, and they will make your life miserable. Okay? Read the golden rules sheet. Majors. More bonds. Question?
But the one that you said is more like the real one with the oxygen still have a little bit.
Yeah, lone pair's there.
So then-
Over here?
Here on here?
Yeah.
Yeah, I should have drawn it. Yeah, it's there.
So would the dashed lines be darker, closer to oxygen?
This is where it's not 1.5. Question like this could be asked. Okay, I said partial plus. Which one has more plus? Oxygen has more plus. Why? Because that's the major resonance contributor. It's like saying, which kid is more, or whatever, ornery. It's called more ornery because dad's more ornery.
So oxygen will be trying to take that electron and holding it longer from the pi bond. So
Oxygen doesn't fully commit and say, hey, let's make pi bond, and I love it. It reluctantly commits.
but if there's a 1+ charge and it's holding the electrons from that pi bond more than the carbon would, wouldn't the carbon have more of the positive?
No, there's more positive here. This goes back to red and white. If this is red, now let's call this white, and this is red. If you mix these, but you get more of this, it's going to be darker pink. The hybrid's going to be dark pink because the red contributed more. We got to move on. Think about it. Okay, do right here. Resonance structures. You can actually show two. There's two resonance structures there. Show them both. Of the three, say which one is major. Where we're dealing with cations. How do you stabilize cations? We can do pi bond towards it. That would give this there. I'm going to go A. The second one is also going to come from this. I'm going to take these electrons and move them in and call that a B arrow. Coming this way, I get that there. Those are your three resonance structures. Which one's major? That one there's major. It has more bonds. Hydrogen has octet. Of the two that are non-major, which one do you like better? Which one do you like better? Well, it can be kind of tough. It's not a good question because that's still a primary cation, even though it's nitrogen. This looks better. Not a good question because they're both primary cations.
So would they be equal in their resonance?
No. That's not going to be a perfect blend. You would just say that this is, the hybrid's going to look like this. You're going to have partial plus here, partial plus here, partial plus here. But it's not like a third. There's more plus where? Yeah, there's more plus here, as illustrated by your major resonance structure. Question?
When you were asking which one was favored of the two, with just one pi bond, is the fact that the first one, pi bond is or the double bond is terminal, that doesn't really have any.
Possibly, I can see. This is almost like a more substituted double bond, but it's a primary cation. It's a tough question. But there are other things that we can use to assess our resonance structures. For example, would you rather have a resonance structure that has a tertiary cation or a primary? That resonance structure would be the better one. Okay? If you were dealing with two resonance structures and the only difference was this one was a tetrasubstituted alkene and this was a monosubstituted alkene, the tetrasubstituted would be your major resonance structure. So we know of other ways to judge structure. How resonance influences regiochemistry? We've actually already done a couple of examples of this. But if you take this here with the alkene and react it with HBr, well, which is your major product? This is an addition of HBr. Are we going to make cation at top or bottom? Well, we can show both possible cations. We make it at the top, and add the new H here, we get that. We add the new H up there and the plus here, we get this. Which cation do you like better? This one, because it's stabilized by how?
Resin.
Stabilized by resonance. We can draw a resonance structure. And you're going to get the resonance stabilized cation. That's going to be your intermediate because it's going to have the lowest transition state leading to it. And so the Br minus ends up attacking there. Now it really attacks the hybrid. But the hybrid still has some partial plus there. Right? If we drew the hybrid, it would look like a bond and a half, partial plus, and your bromine is still attracted there. See, this is difficult to work with. Cumbersome. Let me tell you this, and I'll say it many more times. In the organic too, I'll tell you this. You can always work with any resonance structure in your mechanisms. For example, so this is our final product. We can get there from this arrow. We can also get there from Br minus adding here and kicking these electrons back over to that nitrogen as a lone pair. That's actually the major resonance structure. You can always work with any resonance structure. Don't let anybody tell you you can't. Okay? Either one is real. The real structure is your hybrid. Okay, you can do that one here on your own. Basically, where's the cation going to form? Next to the ring or away from it? Next to the ring. That carbon next to the ring is called your benzylic position. It's going to be resonance stabilized from the ring donation. Things below. When we come back after the test on Tuesday, please have answered these questions over here. Which carbons there and there? Answer these. Ones below, it says show all possible resonance structures. Basically, there's a number of questions remaining here. We've covered basically 90% of this handout already. Please try to answer those questions for Tuesday. Test is on Monday. On Tuesday, we'll be back here. And then when we finish this up, we'll move to the other handout we gave you, which is on diene. Chemistry of diene. We've already seen the resonance of diene. Don't forget SI today at noon. Over in Science Hall, SI, noon to 1. Yeah, it'll be, oh, I'm sorry. Yeah, we'll actually be doing this Monday after the test. Test is 1 in the first hour. SI today at noon.